All right, let's get started with Lesson 9, Neutralization Reactions. Particularly with these neutralization reactions, we're going to focus on strong acids and strong base neutralization reactions in this particular lesson. All right, so this is the idea. When a strong acid and a strong base react, they will always produce the products water and a salt. As shown in this example, where you have a strong acid, it's going to react with a strong base, it's going to produce water and some kind of salt. Let's use the strong acid, hydrochloric acid, and the strong base, sodium hydroxide, and we're going to react them together. Now, the strong acid is going to be the proton donor, so the HCl is going to donate an H plus to the sodium hydroxide, and so essentially what's going to happen is we're going to form water, and the salt is going to be sodium chloride as a result of this acid-base neutralization reaction. Now, why do we call it neutralization? Is because if we add an equal amount of acid and an equal amount of base, so say for instance you add 0.1 molar hydrochloric acid and a 0.1 molar sodium hydroxide, all of the acid and all of the base is going to be completely used up. There will be no acid, strong acid or strong base remaining. It's just water and sodium chloride. So the only thing that will affect the pH then is going to be the water in this case. Now, in some acid-base neutralization reactions, especially if it's a weak acid and a weak base, then often you will form a salt that will also affect the pH. But we're not going to worry about that in this particular lesson. Right now, all we are going to focus on is that all of the strong acid and all the strong base, if they react completely with each other, they will form water, and water will be the only substance that will affect the pH in the solution, creating a pH of 7 then, which of course a pH of 7 is the pH at which we say something is neutral, or we have a neutral solution. All right, we'll focus this a little bit more as we go through this lesson. All right, so again, as we just mentioned, if equal amounts of acid and base are added, then when the reaction is complete, all the acid has been neutralized by the base. The only substance that remains will be water and salt. Now, the pH of the resulting solution should be 7 at 25 degrees C, because at this point, the autoionization of water is the only reaction that occurs. All right, so if you remember, we're going to produce water in the salt. The salt is not going to affect the pH at all. It's only going to be the water, and that is because the water reacts with itself, as you know, and that's going to form the hydronium ion plus the hydroxide ion. So we know that since this is an equilibrium situation, and these are AQs, so the liquid water is not involved in the equilibrium expression. The Kw, the equilibrium constant for water ionization, autoionization, is equal to the hydronium ion concentration times the hydroxide ion concentration. Well, at the terms of this, the hydronium ion concentration should be 1.0 times 10 to the minus 7 at 25 degrees C. All right, that should be the concentration of the hydronium ion. So we know that the pH then, so I'm going to just kind of squeeze this in, pH is equal to the negative log of the hydronium ion concentration. Therefore, if we plug in this into our equation, we should get a pH that's equal to 7. And that's why when we take a strong acid and a strong base and they react in equal amounts so that they completely are used up and nothing is left of them, the only thing then that affects the overall pH will be water, because water reacts with itself and forms the hydronium ion. The concentration of the hydronium ion at 25 degrees C, which is 1.0 times 10 to the minus 7, will give us a pH of 7. All right? Now, what if we start with different amounts of acid and base? Well, in that case, we are going to have one of the reactants, either the acid or the base, is going to be in excess. And so, therefore, whatever reactant is the excess reactant is going to determine the pH of the solution, all right, by that excess reactant, all right? And if there is an excess reactant, the pH should not be 7. So, for instance, if we have an excess of strong acid, then the pH of the final solution should be less than 7. But if the base, the strong base, is in excess, then the pH should be greater than 7. Okay? So let's do some example problems here that shows and indicates these ideas. So here we got a reaction between a strong acid, hydrochloric acid, and sodium hydroxide. And they want to calculate the final pH for this reaction. Well, we know that hydrochloric acid and sodium hydroxide react in a 1-to-1 ratio to form water and the salt sodium chloride. Now, we're going to start out with equal amounts of acid and base here. And since sodium hydroxide and HCl react in a 1-to-1 ratio, they're all ones, 1-to-1 ratio, all of the acid and all of the base is going to be completely used up to form water and salt. So there should be no excess of either one of the reactants. Therefore, the pH then will only be determined by water, since water, again, reacts with itself to form the hydronium ion and the hydroxide ion, and the concentration of the hydronium ion should be equal to the concentration of the hydroxide ion. And in this case, it should essentially, therefore, with equal amounts, should give us a pH of 7. Okay? Because we've used up all of the strong acid and strong base, and the water ionization with each other, autoionization, gives equal amounts of hydronium and hydroxide. Therefore, the pH should be 7, and we have a neutral solution. Okay? But what if we don't have equal amounts, and one reactant is indeed excess? So in this case, example problem 2, again, HCl is going to react with sodium hydroxide. They do so in a 1-to-1 ratio to form water and salt, sodium chloride in this case. And now we're going to start out with a 2.2 molar HCl and only a 0.1 molar sodium hydroxide. So if you determine the limiting reactant here, it should be sodium hydroxide. So that means all of the sodium hydroxide should be used up, and at the end of the day, when the reaction is complete, there will be no more strong base in our reaction mixture. But hydrochloric acid is not going to be completely used up. It's going to be in excess. All right? The sodium hydroxide, it's 0.10 molar. All of that will be reacted with only 0.10 molar of the HCl. So that means that HCl is going to be excess by 0.1 molar. Okay, it's going to have an excess concentration. So that means that when the reaction is over with, we have two things going on. We have the autoionization of water and the ionization of HCl, because HCl is going to react with water. Naturally, the excess, this is the excess HCl. And that the water will be the base here, so we're going to form the hydronium ion plus the chlorine ion. All right. So if I have 0.10 molar of this, then all of that should be converted into the hydronium ion, since it's a 1-to-1 ratio here. Okay. So all of the excess will then be ionized into the hydronium ion. Remember, strong acids, which HCl is, completely ionize or dissociate in the presence of water, which is the base. All right. So the only other reaction going on is water ionization, autoionization, to form hydronium ions plus hydroxide ions. Now, the hydronium ion here for this concentration is only going to be to the -7 power. So that's really small compared to the 0.1 molar. So the pH is really going to be dependent here on the excess reactant of HCl and not on really the autoionization of water. Even though that still occurs, this is still happening at the end of the reaction. By far, the excess reactant, as it's reacting with water, it's going to produce a larger concentration of hydronium. So therefore, we're going to determine the pH based off of that. So the pH is equal to the negative log of the hydronium ion concentration. So pH is equal to the negative log of 0.10 molar, and therefore that should give us a pH of 1 when we do the math. Okay, so definitely much lower than a pH of 7, which we would expect because we have quite a bit of strong acid left over. It should be affecting the overall pH. Okay, so that's kind of an example of how the excess reactant affects the overall pH in an acid-base neutralization reaction, if there is a limiting and an excess reactant. Now, if this was turned, and tables were turned here, and the sodium hydroxide was in excess, then we would assume that the pH would be much higher than 7, and it would be a basic solution overall. Okay, so anyway, that's it for this particular lesson. We're going to wrap it up now. Make sure that you spend some time studying these notes and understanding the strong acid, strong base neutralization reactions and how to calculate the pH for them. Right?